So I guess we can start. Thank you. Thanks for everybody to coming to join us. We are starting a new reading group now. The basic topic is for using machine learning for molecule simulations and sampling. And by the way, I'm Jiajun from University of Cambridge. And this reading group is supported by the UK AI Hub in Generative Models. And this is organized by Tony, Chen, me, and Lucas and Christiana. And Tony, would you want to say hello to others?
Hey guys, I'm Tony. Yeah.
And Tony's internet is not quite stable, so I will do this introduction. So it's actually our first time to do this reading group. So if you have any suggestions, questions, or requests, don't hesitate to reach out. We're happy to listen to a different voice. And we're aiming for a bi-weekly reading group. And our topic we aim for a large varieties of topics, including molecule simulations, sampling methods, Boltzmann generator, Boltzmann emulator, or even like diffusion models, generative models for modeling molecules or other things. If you have some work you want to present, just let us know. And so for the first reading group, we are very happy to have Professor José Miguel Hernández-Lobato. He will give us a talk on free energy estimation. He is a professor in University of Cambridge. He has very spread interest in Bayesian machine learning, meta-learning, Bayesian deep learning, probabilistic compression, and molecular design, simulation, and also sampling neurosamplers. So I will give time to Miguel.
Good. Thanks. Let me share my slides. Let's hope this works. Good. Let me see if this works as well. Full screen. Yeah. Great. So I think you can see my slides now. Is that right? Great. So yeah, I wanted to present this work on FEAT, free energy estimation with adaptive transport. And this is work done in collaboration with Yaojun, Yanchi, Francisco Vargas, Yuan King, Carla Gomez, and Eric van den Eingen. And I have to say that my contributions here were not that much, but most of the work is here due to Yaojun and Yankee and collaborators as well. But yeah, I'm really excited about this work, and I think it's really interesting, and it's a good way to connect between the areas of machine learning and molecular modeling and simulation. And I'm going to start with some motivation for what we are interested in doing. Imagine that we may have a new drug-like molecule, like the one shown in this screen here, and we may want to know if this molecule is going to mix with water molecules or not. It's going to be staying apart, like in a state B, or it's going to be happy to be surrounded by water molecules. And this is a very important problem in drug design. If you want to design new drugs, you want to design molecules that are soluble and they're going to dissolve in water. And if your molecules don't do this, they won't be working effectively as drugs because they won't be able to be taken by people, and they won't go into your bloodstream, for example. So we want to know this, and the question is, how can we know what's going to happen in the real world? What we can do is then look at the energies that the molecular configurations can take in practice. So you could have in this variable x here, we would have this variable x and the water molecules and the drug-like molecule. They can have different energy values for different configurations. And given these energy values in state A or state B, we can obtain the corresponding probability distributions by taking the exponential of minus the energy and times some normalization constants that would be here. And these normalization constants, these are the log normalizers of the distributions. They represent the probability mass for each distribution, okay? So this would be this probability mass here. Let me write it here. This probability mass is going to be exponential of f a, for example. And the same thing is going to happen with the other distribution. So to know what's going to happen in practice, if the molecule is going to be happy surrounded by water molecules or not, we need to look at these probability masses for the two states. And if one is way higher than the other, that's what is going to happen in the real world. We're interested in particular in this relative probability mass associated with each state. And you can write this as this difference between log normalizing constants for the distributions, and this is often called the free energy difference. Okay, we're interested in calculating this, and there is a way to do this estimation of the normalization constant. And the idea is to take these distributions, one for the first state, the molecule surrounded by water molecules, and another one for the second state where the molecule is separated from the water molecules. And we can create a sequence of interpolating distributions, P2, P3, P capital N minus 2, and so on. And we can generate samples from these interpolating distributions. We can generate this data where we have that maybe a total of N samples, capital N samples for each of the distributions, and we have a total of these M distributions. It turns out we can easily calculate the normalization constants of actually all these distributions, including the ones that we care about, P, PA, and PB. We can estimate the normalization constants by running a method called MBAR, which is the state-of-the-art method for solving this problem. And the idea in MBAR is very simple. You could imagine that you have samples, maybe from this first distribution, P1. You may have a few samples like this, and you may have also some samples as well. I'm going to write them with circles. You may have also samples from P2, okay? And the samples from P2 will be in this region of space. The samples from P1 are in this other region of the X space. This would be the X space here. So estimating the normalization constants of these distributions is the same as determining the height of the curves that I show in this the right height of the curves once they are all normalized to be 1. And you can understand, you can solve that problem very easily given the samples by solving a classification problem. Okay, if you want to solve a classification problem that separates the crosses from the circles, the optimal classifier is going to be given by the right density ratio between the distribution P2 and the distribution P1. Okay, and this is basically what MBAR is basically doing, is trying to solve a classification problem, not with these only two samples, but with samples from all the different distributions, trying to guess from which distribution the samples were actually generated. You have a total of capital M categories, and you have to guess for each sample which category the sample belongs to, from which distribution the sample belongs to. And it turns out that if you have a model like that, you will choose the right height for the distributions when when you are able to solve this classification as well as possible given the observed data. So if you maximize the likelihood of a model where the only parameters free are the height of these distributions, you will be able to estimate that right height by maximizing the likelihood. This is what this method MBAR does, and you can understand it, as I said, as a maximum likelihood solution for a generative classifier predicting from which distribution each of the sample belongs to. Okay. If you solve that maximum likelihood problem, you will get an update. If you try to solve that problem by setting the gradient of the log likelihood to 0, you will get an update for the log normalization constant of each distribution of this form. And it says that the log normalizer of the mth distribution depends on the log normalizers of the other distributions according to this expression. And you can then estimate the log normalizers easily by first initializing them to some value, for example, 0, and then iteratively updating the log normalizers using this expression above. Okay, you only update, for example, maybe all the log normalizers except once, because you can only estimate the density ratios up to a constant. And at convergence, this free energy, or the difference between log normalizers, you can obtain it by just calculating the differences between the estimated log normalizers for the first distribution and the last one. Okay, so this is great. MBAR is actually the state-of-the-art problem to estimate these free energy differences, and is guaranteed to have a minimum variance, which is great. But sometimes maybe we may not have access to samples from intermediate distributions. Okay, imagine that maybe we only have access from the first initial distribution and the second one, and we haven't generated samples from intermediate distributions. Generating these samples can be expensive depending on the type of simulation that you do. And it could be that maybe it's very expensive to generate the samples and you only want to generate samples from the two extreme distributions and not for the intermediate ones. And here we're going to see methods that will allow us to solve this problem where we don't have the intermediate distributions. Just one thing to mention, in MBAR, it's important that there is overlap between these distributions, because you need to solve the classification problem, and your optimal classifier will converge to the right density ratio given the observed data. And for that, you need the data to overlap so that you can estimate the right density ratio to solve the classification problem. If there is no overlap, this method is going to struggle and it's not going to work well. And one of the problems that we will have when we have only samples from the two distributions is this lack of overlap. Okay, so just some introduction to some notation that I'm going to be using later on. We are going to have now these probability distributions that are exponential of minus the energy, and they are not normalized, and that's denoted with this tilde symbol here. This represents the normalized distribution. The normalization factor of the distribution, we are going to call it Z, and the free energy is going to be minus the logarithm of the normalization factor, the normalization constant, and the free energy difference is going to be the difference between those log normalizers, or the minus the log of this ratio between Z2 and Z1. Okay, so how can we solve this problem when we only have samples from A and from probability A and probability B? The right way to estimate the normalization constant can be by importance sampling. And this is what this method called free energy perturbation does. And it's just as simple as follows. The free energy difference is given by this expression here. And you can just replace Z2 by the normalization constant of the second distribution. And then you can multiply here and divide by P1 and normalized. And then you can take this normalization constant Z1, dividing P1, and that's the normalized first distribution. And then later on, you have this ratio between a normalized distributions P2 tilde and P1 tilde, and that's just the exponential of these differences between the energies, the energy of the first distribution and the energy of the second. And this integral with respect to the first expectation of the exponential of the differences in energies. Okay, this is important sampling, and it works well if there is low variance in this in this quantity that you are averaging, this exponential of minus the differences in energies. But in practice, you can have high variance. Okay, and this is a problem with important sampling. Important sampling can in general have very high variance, in practice even infinite variance. So if you have estimators with infinite variance, that's not great. Okay, one way to improve over important sampling is to use another method called Bennett acceptance ratio, which is just similar to MBAR, but only for two distributions. Okay, it's also a minimum variance method, and it's very similar to MBAR in the sense that you have your free energy difference here, and you estimate it at this as this expression shown on the right, which depends on this quantity C, which is a guess of the free energy difference. And the minimum variance is achieved when C is the right free energy difference, and then this function G here is Fermi's function, which is similar to the logistic function, but without the minus sign here. So it's 1 divided by 1 plus exponential of x. So bar can be shown to have way less variance than important sampling in general. And it works as MBAR using this iterative approach where you initialize C to some value, and then you update your estimate of the free energy difference, and then you update C and you iterate, okay? And this can have a way less variance than important sampling, but it can still struggle if there is no overlap between distributions. It's the same thing as what I mentioned with MBAR. No? MBAR, you need to solve this classification problem where you need to guess where the samples come from to estimate the right density ratio. And here is the same. And if you don't have overlap between the samples, then there is no way you can estimate the right density ratio. So you need to ideally have overlap between distributions. And this can be achieved by doing some transformation of the samples from one distribution. So we may have here samples from the first distribution, P1, they will be in this region of space. There is not a lot of overlap with the samples from P2 in red, shown here, but you can do a transformation of the samples from P1 to obtain a new set of samples that are distributed according to P2 and that are going to have higher overlap with P2. Okay, you obtain this P1 prime distribution of samples, and there is like a higher overlap. Typically, this transformation, you want a transformation that is flexible enough, and you typically want to learn that from data, and one technique is to use flow matching for this. And flow matching or a continuous normalizing flow is more or less the same thing. You just say that the distribution of the data at, for example, some time, you will transform your data in this way. You will have some vector field U that is going to tell you how you transform the samples, okay? And to obtain the transform samples, you just need to integrate this. Let me delete this a little bit. This would be U, okay? And the interesting thing is that you can get the density of the transformed samples, you can have the log of P t of x t. This is going to be equal to the log of P0 of x0. X0 would be where we start our samples, and then there is going to be here an integral. And this is going to be now some operator operating on this. This is some t here as well. Okay. US, XS, DS. Okay. And if we want the density of the transformed samples, we need to solve this integral. And this is a divergence operator. It's going to be the sum of the diagonal entries of the Jacobian of this function, US, and that can be quite expensive. And this means that calculating these changes in the density due to the transformation with this method can be very expensive in practice. You need to calculate this divergence of the transformation of this vector field given by UT. And if you have a neural network modeling UT, then that's going to be quite expensive. So ideally, we want to do something different. And what we propose in this work is an approach that is going to allow us to calculate these free energy differences at a lower cost and better than these previous methods. Okay, we want to have high overlap, so we want to transform the samples between the two distributions A and B so that there is high overlap, and we're going to do that using stochastic differential equations. Okay, we're going to have this stochastic differential equation that is going to start at a sample here from the first distribution A, and it's going to be given by this expression, and is going to drive the sample towards a region of space at time 1 that has high overlap with the probability of P. Okay, and we're going to have also a backward SDE, which starts at a sample from the second distribution PB, and it's going to be running backwards in time according to this expression until we reach time 0, and at time 0 we get something that is going to be close to the distribution PA. Ideally, we want these SDEs to actually map exactly samples from PA into PB and from PB into PA. And these SDEs have some drift coefficients here, and then some diffusion coefficients here. And the drift coefficient has a gradient of this function u, which is actually the energy of the marginal distribution for the samples generated by the pair of SDEs. Okay, and we have also a control term given by this u. So this would be the gradient of this energy that appears here, and then we have a control term here u that is going to guarantee that the samples generated by the SDEs have the right energy. The marginals that are generated at the different time values by these SDEs, they have the right energies. And obviously, I didn't mention it, but this is the Brownian motion that appears here, and then that appears here. And the arrow denotes the direction in which you solve the SDE. The interesting thing is by using these SDEs, we are going to be able to calculate this free energy difference without having to calculate these expensive changes in density as we had to do in the continuous normalizing flow example. So in this previous case, we had to calculate this integral here. That's going to be quite expensive, and we're going to see that using these SDEs, we can sidestep that. Good. This is just an example of how this works. You could have a distribution PA here on this side, and we see the trajectories of the SDEs that map the samples into the second distribution PB, and obviously these SDEs can be run forward or backward. and you obtain this interpolation now between the two distributions with a lot of overlap, ideally. I didn't tell you yet how you get these SDEs. We're going to see that later, but we're going to assume that we have these SDEs and that they allow us to transform the samples in a way that they have high overlap. You can then calculate the free energy difference in a simple way by first discretizing your SDEs. So you will assume there is a discretization of the time. The SDEs run from time 0 to time 1. Time 0, you have samples from PA. Time 1, you have samples from PB. And you can now discretize this unit interval and get some time values T1, T2, T3, and to Tm in this unit interval. And then you can simulate the SDEs in this discretized space very easily by just calculating the drift terms. So the next value for the SDEs, obviously you start first with a sample from PA. You have samples from PA. You can start with a sample from PA here. This would be your initial sample, and then you evaluate these drift terms given by the gradient of u and lowercase u by these functions. You can evaluate the drifts, and then you can add some Gaussian noise with this standard deviation to those samples, and you will get the new value for x. You can do this following the time points that you chose in your discretization, and eventually you will get now with a value that is approximately distributed as PB. And you can do the same thing backwards. You can start with a sample from PB at time value 1, and then you can run the backward SDE, which has its own drift given by these terms. This would be the mean of the next sample from the SDE. You start with a sample from PB here, you add this constant, and then you add Gaussian noise with this standard deviation, and you will get the next point. Okay, so now you have like this discretization in the forward and the backward direction, starting from samples from PA or PB. And then you can estimate the free energy difference just using importance sampling. But now, instead of working on samples directly in the original space, now you work with all the samples that you generated in these discretized trajectories. Okay, you can start with samples from, this would be an expectation with respect to the sample generated in the forward direction. This is in the backward direction. You can use importance sampling. You are sampling now from the forward SD. So here you have the probability distribution for A without normalizing that. This is the density, the normalized density for PA. And then this is the density, the Gaussian density of these updates that you do by solving the SDE forward in this discretized space. And then here in the numerator, you have exactly the same thing, but for the backward model, okay? The backward model starts at a sample from PB, a normalized, and then you have now the Gaussian transitions given by this discretized SDE. And if you calculate the expectation of this with respect to the samples that you obtain in by solving the discretized SDE forward, you actually get the ratio between normalizing constants. Okay. So and minus the log of that is going to be the free energy difference. Okay. And obviously you can do this by doing importance sampling with samples from PA, which is what we do in this first term, but you can do it with samples from PB, which is what you do in this second term. Okay. And yeah, both using an infinite number of these importance sampling importance samples, then you would be able to obtain an estimate of I mean, you would obtain the exact free energy difference. In practice, these expectations, you could replace them with empirical averages. Interestingly, you can also call W the log density ratio between the forward model and the backward model. So you calculate the density ratio between the probability distribution that the forward model would give to one of these trajectories of the SDEs, discretized SDEs, and divided by the probability density that the backward model would give to that. And this can be shown to converge to something called the generalized work, which has been also, it represents how hard it is to transfer the samples from PA to PB through these SDEs. And it appears also in other methods that we're going to see next. Good.
Can I ask a question here?
Yes.
Here, are you assuming that the control is perfect in the sense that the marginal distributions of the XTs are following precisely the UTs you've set for yourself?
You don't need it.
Okay.
Here you don't need it because you just have like this doesn't have to be exact.
Okay.
But obviously, ideally, you want to have a good control. I mean, you want this control to make this forward and backward model as similar as possible, because that's going to reduce variance in important sampling. But it doesn't have to be the case. If that's not the case, then you will have high variance, and that can be not so great. But yeah, in principle, you don't need these expressions are accurate even if your control is not perfect.
Good. Okay, thank you.
Good. Similar things have been done in the past, and for example, there is this method called the Skvortsov-Jasinski equality, and the idea is to also use a forward SDE to map samples from the distribution A into those of B, and you can also obtain the generalized work, but in this case it's given with this other expression, which is now an integral, and here you have this divergence also of the vector field UT, which can be expensive to calculate in practice. And the free energy difference would be by the same expression that I mentioned before. You will have the same log expectation of the exponential of minus the generalized work. This calculation of the free energy difference using this value for the generalized work can be more expensive in practice because you have the divergence. And the previous method has the advantage that you don't need to calculate this divergence. You just need the density ratios. There is this work also by another Cambridge student, Francisco, and others, including one of my students, Reyes. And they propose this controlled Crookes fluctuation theorem. The idea is also to use the forward and backward SDEs. And you can then show that the free energy difference, sorry, this should be lowercase here, is going to be obtained through this density ratio, but it's not a density in this case. Here you will have path measures. This would be like the probability, the measures for the trajectories that the SDs generate in the forward and in the backward direction, and you can calculate this ratio between those measures. This would be this is often called the random Nikodym derivative. And you can show that this equality holds, but here you're assuming trajectories with an infinite number of steps. Obviously, you can discretize them. It's more or less the same as what we have mentioned before. So this method is not really that new to calculate the free energy differences in this way, but here you are doing important sampling. And what is more new is to actually then not do important sampling, but we have seen that MBAR and BAR, they can be more efficient by estimating these normalization constants, solving a classification problem. And you can do exactly the same thing here. The only thing is that now you are going to use a bar style approach, but to estimate the free energy difference using now samples that correspond to trajectories from the discretized SDs, okay? And in the same way that we are doing now here importance sampling in the previous estimator, now you can apply the same bar style algorithm where you're going to start with some initial guess for the free energy difference. And now here you have a similar update rule as the bar style that we mentioned before, but you operate on this generalized work evaluated on, I mean, it would be just the log density ratio between the forward and the backward model. And this is actually easy to calculate. And this is going to reduce variance quite a lot. So instead of doing just importance sampling on this, using these density ratios from the forward and backward models directly, we can just run a bar style estimator that is going to have less variance. If you think about it, it's like as if you wanted to solve a classification problem between trajectories of the two SDEs in the forward and in the backward direction discretized, and you want to guess if the trajectories were generated by the forward SDE or the backward SDE. Okay. So this is basically the key thing here, and this is going to give us a much more efficient estimation of the free energy difference. What I didn't tell you is how to learn the SDEs, because initially you only have samples from the A distribution and the B distribution, and that's what we are going to have. We can learn these SDEs, in particular the vector field U and the gradient of the energies, using the framework of stochastic interpolants. The idea is to create now samples from the SDEs, and we can actually do that very easily. We can take now, we can generate samples by first sampling one point XA from PA, sample another data point XB from PB, and then we are going to sample Gaussian noise, and we will do an interpolation between the samples with some coefficients alpha t and beta t that guarantee that at time 0 we only have XA because alpha 0 is 1 and B 0 is going to be 0. And at time 1, we are going to have just XB because alpha 1 is 0 and B1 is 1. This allows us to now generate samples XT that have the right distribution at time 0, the right distribution at time 1, and they're going to interpolate in between. And we have some Gaussian noise, which is going to allow us to learn the score, which is precisely what we need here. The gradient of the energy is going to be related to the score, and we can estimate that using denoising score matching and other techniques used in diffusion and other models. And the drift term U, you can estimate it also quite easily because it's going to be equal to this expectation of the derivative of the interpolant with respect to the time variable, and we can do that right away. And we could estimate this conditional expectation by minimizing a squared error loss, and the same thing for the score. Good. So we can use these methods to learn now the SDEs, and we can see how this works in practice. This was validated on some experiments on different problems. We have first a problem with mixtures of Gaussians, and in this case you have two different states. The first state corresponds to a 16-dimensional 16 component mixture of Gaussians, and then a 14 component mixture of Gaussians. The other problem is going to be given by a Leonard-Jones system where we have now particles where in one state there is a Leonard-Jones potential affecting the particles, and the other one is without the potential. Another problem is with this alanine dipeptide, which is a common molecule used in benchmarks, and you can have it in one state the molecule just in vacuum, or in another state, the molecule in some implicit solvent. And obviously that represents two different distributions for the configurations of atomic positions of the molecules. And the other problem is a version of this alanine dipeptide where you have two states. One is when the molecule it has some configuration where the dihedral angles are in this mode. Here in the center, I mean, where this phi, not the mode, but when phi is in this range, this would be one of the states, and the other state would be when the atomic configuration corresponds to a value of phi that is not in this interval. We compared with different methods. The first one is a reference, which is just obtained running MBAR with these intermediate distributions that can give you like very accurate results if you have several of these distributions. We compare with the target free energy perturbation. This is a method based on this flow matching technique that I mentioned before that is more expensive. And for example, in these problems, for Leonard-Jones, where there is a large number of particles, then this method is not scalable and it's very expensive. We compare with neural thermodynamic integration, which uses a diffusion model learned from data, and then so you learn some energies of the samples generated with diffusion, and then you use those energies to estimate the free energy difference. I didn't have time to describe this method in detail, but I mean, it's a common baseline. It's a recent baseline in the literature. And we include results for our method here. And we see that our method produces results that are very close to the reference given by MBAR in these problems. And we have also good results in the alanine dipeptide problem, producing values that could be said that are closer to the target as well. Good. What is interesting is to look at the gains that you obtain by using this minimum variance estimator, using this bar-like method to estimate the free energy difference, using this forward and backward discretized SDEs. And we compare with just importance sampling. This is for the Leonard-Jones problem with 128 particles, and with the alanine dipeptide and we see that the estimator with minimal variance converges in blue, converges very quickly to the ground truth value shown in dashed lines, and the importance sampling estimator is having much more trouble to converge to the right value. In particular, the convergence can be very slow, as in this case. And this would be the x-axis is the number of mini batches processed through training. So we can see here that you can converge quite quickly as compared to the importance sampling estimator with not a lot of training. Good. So this concludes this. We have seen here FEAT, this free energy estimation method with adaptive transport. It calculates free energy differences using only samples from states A and B. It doesn't need these samples from intermediate distributions. Uses the stochastic interpolant method to learn these SDEs that are going to map samples from one distribution into the other in a flexible way. It avoids to calculate expensive changes in this density, as you would need to do with continuous normalizing flows and in flow matching. And it reduces variance by using this bar-like style estimator. And we have seen that it outperforms other baselines like this neural thermodynamic integration and neural target FEP. And one of the limitations is that obviously you need to have the samples from the distributions A and B, but then you need to train your SDE models, and this will have some extra cost. And also in large systems, you need to be careful because your SDE models might not be accurate enough to do good transport of the samples, and you can still have high variance. If there is no good overlap, between the forward and backward SD models, then you can run into problems. Good, that's all. Thanks everyone, and I'm happy to answer any questions. If anyone wants to ask anything, I think Yao Yun and is also here, so he can also help with the questions. If there is anything about the technical parts, he's probably the best person to answer those. Good. Any questions? Anyone wants to ask anything?
I can ask another question.
Yes.
So thank you very much. Very nice and a very nice presentation. So I remember that also with normalizing flows like that work with discrete maps, some people have done bar. I mean, there is a paper called Deep Bar, for example. Do you think using SDEs will give us like more scalability, or have you compared? Have you looked into this direction as well?
So by discrete, you mean discrete flows where you just have like, instead of the continuous normalizing flows, there's some fixed transformation there. I mean, yeah, so you could have something like that. I mean, people have used flows in many different applications. My experience with discrete flows is one of the difficulties or the problems with that is the lack of flexibility. Typically, the discrete flow models, they will have less flexibility than discontinuous normalizing flows. And I think that can be a limiting factor. We didn't really compare with that. Obviously, you can, yeah, instead of the continuous normalizing flows, you could have discrete normalizing flows. I think probably in simple problems that could work fine, but maybe in more complicated ones where it's not so easy to transport the samples, those methods could struggle. But I don't know, we didn't really compare with those.
Okay. Thank you.
Good. Any other question?
Yeah, it's a similar question, the same realm, I guess. As I saw, like recently, people started using like in the Boltzmann generator field, people started using like discrete flows and stuff to like generate some proposals, and then kind of in normal Boltzmann generators, you like, generate some proposal, you know it's not great, right? And then you somehow importance sample your way to the kind of okay sample. People start using some like transport, etc. there as well with discrete flows, etc. What do you think? How does your approach compare to that? Like Boltzmann generators in general, and what do you think could be like limitations and weaknesses? I guess Boltzmann generators are hard to scale. Do you think yours is more scalable, or what are some pros and cons there, I guess?
Yeah, I mean, I think there is like many things there. I think the Boltzmann generators, they have been used yeah, in practice to do this generation of samples. So you are given some, you will have the energy, and then you want to generate samples from a distribution that has that particular energy value. I think the problems are slightly different in where you apply these Boltzmann generators. And here we want to estimate these free energy differences. I mean, you could obviously use Boltzmann generators to do that, but it would be a bit more or less what I mentioned before. If you use the normalizing flows, you could use normalizing flows to generate the samples, but then the main problem is the flexibility. And obviously you can go to the continuous case, but then there is a lack of scalability because you cannot calculate the density of the samples easily.
Yeah, makes sense. I guess like in practice, people often go from then samples to end differences, I guess, with these generators. But yeah, I see your point. That makes sense. Thanks.
Good. Any other question?
Hi, thanks for the presentation. So I have one question. Is this method transferable, for example, across different molecule systems or even different thermodynamic states?
Yeah, that's also, yeah, I mean, yeah, I didn't say much about that, but one of the promising things of this is that obviously if you have some transfer, that would be great because then you don't really need to retrain your models. That can be expensive. And you only need to generate samples from the SDEs, and that can be done at a lower cost than if you have to generate samples directly in other way. I didn't say that, but imagine that you maybe have a collection of problems and you learn your SVEs. Let me show the models. Maybe you learn these SDE models conditioned on some properties of your problem. I mean, the example that I mentioned before, no, maybe you want to know if a molecule is going to solve in water or not. You could think about learning an SDE model that is conditioned on the features of your molecule. Okay, and then maybe you train on many different molecules, this SDE model, and then you get a new molecule, and you may want to estimate this free energy difference. Then you could generate samples from the SDE model to estimate the free energy difference, and you could reuse the models that you learned already. And maybe the learning could be expensive, but you only do it once. And if the models can transfer, then that would be great. We didn't really do experiments on that. I think that's on our to-do list. I think it would be great. My impression is that I don't see why, if you have enough data and you have flexible enough models, why wouldn't you be able to learn SDE models that transfer from one problem setting to another? I think in principle it should be possible. But yeah, I think it's something that we need to test next.
Yeah. Okay. Great. Thanks.
Good. Any other questions? No? Okay. I think then we can leave it here. Thanks everyone for joining, and I hope to see you in the next edition of the reading group.
Yeah, thank you so much. Thank you, Miguel. And also thanks for everybody to coming and join us. And by the way, we have a Slack channel. If you want to stay posted, please join the Slack channel. And this is a bi-weekly style reading group. So the next session will be 2 weeks later. We will have Professor Gabor to give a talk. So yeah, thank you very much. See you guys. Thank you. Bye-bye.
Bye.